thank you so much for coming today. I really appreciate all your support. As you know, my name is Sierra Monreal, and my summer research involves the investigation of flexible perovskite solar cells for space applications. Thank you to my faculty mentor, Dr. Nicholas Rolston, and my graduate advisor, Savanith Panikula. Flexible perovskite solar cells, also known as PSCs, are very versatile devices. They offer solutions to a variety of spaces. However, I'm going to be focusing on the space applications. These devices are very adaptable, low cost to manufacture, lightweight, powerful, and transportable. My research goals for this project were to fabricate sustainable, flexible perovskite solar cells, characterize their electronic and ionic properties, and conduct stress tests to see how they would perform in rigorous environments such as space. The manner in which I went about this project was to translate the pre-existing knowledge and research from PSC fabrication on rigid substrates to flexible substrates. To put this into a larger picture, us Arizonans are no stranger to solar panels. As you all know, it's very sunny here. We see them on the rooftops of houses, buildings, parking structures. They're essentially everywhere. Now think of a satellite. I bet you think the first thing you thought of was the cylindrical body with two wings out on the sides. These wings are rigid solar panels that are extremely heavy, costly. The reason why I want my research to be successful is because it will reduce the cost and weight of these solar panels in satellite and space devices, in which the flexible solar panel could possibly go around the body of the cylindrical device instead. So the specific perovskite that I used within this research is called methyl ammonium lead iodide, also known as MAPI ink. The relevance of using this specific perovskite is because it has a large absorption coefficient due to its crystal structure. You can see its crystal structure in figure 2. And the relevance of it having a large absorption coefficient is because it can maximize the current output. Previous research demonstrates that MAPI proves to be effective on rigid substrates, so we are hoping that it is the same on flexible substrates with minor adjustments. As you can see, figure 3 is the fully combined MAPI ink perovskite itself. And the components of this recipe consist of powder precursors and solvents. The powder precursors being methyl ammonium iodide and lead iodide. The solvents being DMF and DMSO. As far as fabricating the device itself, which is MAPI, the perovskite, on the polyethylene terephthalate, which is also known as PET. First step in this process is using the sonicator, which essentially just gets rid of the debris on the substrate itself, and it uses sonic waves to shake off the debris almost. And we submerge the substrate in solutions known as extran, which is industrial grade soap, and IPA. The next step in this process is using the UVO cleaner. Through putting substrates in this UVO cleaner, it uses a combination of UV and ozone to allow the perovskite it prepares the sample to allow the perovskite to adhere to it better. And this is essential for the next step in this process, which is spin coating. So this is just the step where I deposit the perovskite and the anti-solvent on the substrate itself. And the manner in which this spin coater works is that there's a substrate that we have and there's a vacuum, so that when the substrate is spinning, it doesn't fall off. And so the reason why this works is because it uses centrifugal force to create a uniform thin film. So when the perovskite is deposited, it can evenly create a uniform surface. And then finally, the last part in this step is annealing, which allows the device to fully crystallize due to extended exposure to heat. So there were many variables that I changed within the perovskite solar cells. Fabrication, these were all the variables that I changed. I'm not going to list them all, but some of these things I used to thicken the film, modify the crystallization process, remove the perovskite in preparation for a later process or a later measurement that I'm doing. But I especially want to discuss the self-seeded growth process, which is essentially depositing the perovskite on the substrate twice in 2 separate spin cycles. So that was a new development that I found kind of towards the end of my research. After fabricating the device using the spin coater, we wanted to determine the quality of the film. So we used an optical microscope, and this is just a visual confirmation that our film is uniform. So as you can see, there's desirable samples, which is shown in figure 9. There's little to no defects, there's no holes, and there's no places where you would assume where it would not be conductive. And there's poor quality samples, which you can see in figures 11, 12, 13, and 14, where there are visual deformities and irregularities, and this would lead us to think that maybe this device won't be effective during electrical and ionic testing. I also ended up using photoluminescence spectroscopy. So essentially the way that this works is that it measures wavelengths of light by projecting a laser of photons onto a sample. And based off how much light was received back into a sensor on this device, we were able to, it was able to generate a wavelength, which is essential because this way we can determine band gap width. And the relevance of the band gap width is because it determines the portion of the solar spectrum that a solar cell can absorb. And I use this, in order to calculate the band gap width, I use the Planck relations, which is a constant over the specific wavelength that the graph generated. Finally, now onto the actual characterization part of these samples. I used a specific device called PIOS, which is essentially an all-in-one characterization tool. I used these for 2 measurements, one being the current voltage measurements, the IV measurements, and the transient dark current measurements, also known as TDC. As you can see, figure 16 is just a setup of what the device looks like loaded into the PIOS machine, but figure 17 just kind of allows you to physically see what's going on in the process right now. So we have the PET, which is essentially like a flexible plastic, the ITO coating, which is a more conductive coating that comes on the PET from the manufacturer, and then we have the perovskite film, which is we deposited it during the spin process, and then we have the carbon electrode, which is essentially just a contact point for these 2 PIOS probes. One of them is negative and one of them is positive. All right, interpretation of my results. I took some previous research done by Vineet Pandukula, and he did testing on the MAPI perovskite on rigid substrates. So he determined what samples would be desirable and which ones would not be. So let me just explain what we want to look at in the results so far. We have A and B. A demonstrates that this device would perform like a semiconductor rather than a resistor. B demonstrates that it has ionic conductivity, as indicated by this little drift current right there. C and D are not desirable examples because it demonstrates that this device is acting more as a resistor rather than a semiconductor, and D just demonstrates that this device does not have enough conductivity to produce an ionic drift current. So figure 19 was actually the most successful sample that I got, and this is important because this result was obtained through fabrication of the self-seeded growth process. Like I mentioned earlier, it was just depositing the perovskite twice in 2 separate spin cycles. So as you can see, it does have a little bit of a curve, but it is not quite at the point where it's acting like a semiconductor. At this point, it's more acting as a resistor. All right, and then figure 20 is another sample that I produced earlier in the summer, and it did have enough ionic conductivity to produce a drift current, as you can see right here. So through using a calculator, we will able to calculate the mobile ion concentration. However, this device right here, figure 21, actually correlates to the previous slide, the figure 19. It correlates to figure 19. So this just demonstrates that once again, it was acting as a resistor and it doesn't have enough conductivity to produce an ionic response. Therefore, we were not able to get a mobile ion concentration calculation. As far as my future plans, I really want to improve the consistency of the fabrication process of the MAPI perovskite on the PET. I really want to get consistent measurements, the IV measurements, and the transient dark current measurements, as well as I want to continue calculating the mobile ion concentration. Now, the relevance of this is that it demonstrates that it's crucial to industry and mass manufacturing for commercial applications. I eventually want to minimize the mobile ion concentration because minimal ion concentration minimizes the degradation of these samples. Yes, and then I also want to complete stress tests to see how these devices would perform in a rigorous environment such as space. So as you can see, figure 22 represents the different patterns in which I would bend the substrate itself before measurement. And I also want to expose different samples to the heat to represent the different extreme temperature heat cycles that it would be experiencing in space. That's my word excited. My acknowledgements are Dr. Nicholas Ralston, Beneath Penicula, Jessica Howard, Ralston Labs, the Intel Mindshare program, the National Science Foundation, and NCI Southwest. Finally, before I finish my presentation, I have a very exciting announcement. So I was chosen to continue my research. I was chosen to continue my research through the funding of the NASA Space Grant Program, and I'm really excited to continue research on the MAPI perovskite solar cells with flexible substrates and work on this throughout the year. So I'm very excited about that. Any questions? Yes, Chase.
Congratulations on the NASA Space Grant. That's awesome. Kind of curious as to if you were to implement this on NASA's next rocket to space. Overall, what are some of the things that that rocket would be improved on compared to the last one? If that makes sense.
Yeah. So, if my device were to be implemented on a next satellite or a space device, hypothetically, we could wrap this around the entire device so that there would, no matter where the sun would be, there would still be some certain exposure to the solar panel itself, and it would still be able to generate energy no matter where the solar panel is, because it's fully encased in this this flexible solar cell. So I think that would be better and more efficient compared to what they have right now, because right now they just have like flat devices, and it takes energy to move them towards the sun. But if it was just already encased in everything, then it would be able to be more efficient in that sense. Yes?
What did you find to be the most challenging part of your research project?
Let me think. Honestly, I think the most difficult part was going through the trial and error. My whole summer was just trial and error over and over and over again. And at certain points, I did feel stuck. I wasn't really sure how to proceed at certain points. I didn't really feel like things were working at a certain point. However, through discussions with a variety of different people inside and outside the lab, and doing research of my own, I discovered that self-seeded growth process, and I was able to make some changes, do something out of the box, and implement that, and it ended up kind of working. So we're getting somewhere. So that was the most difficult part, really persevering through that trial and error process.
Did you have a favorite part of your research project?
What did you say?
What was your favorite part of the research project?
I really liked using the spin coder because you need a certain amount of, like, you have to have a specific skill set in order to fabricate the devices properly and create a proper coat on a sample. So we deposited the perovskite using a pipette, so you have to find the right speed at which you disperse the solution. So if you went too fast, it might create deformities. If you went too slow, it might create deformities. If you didn't put on the anti-solvent at a certain part of the cycle, it might not work as well. So it was very technical. It was challenging to try and perfect that sort of process and that skill set, but I think it was pretty fun because it was very hands-on as well. I'm a hands-on person, so yeah. Anything else? Ego?
Are you the first one who has attempted to investigate this search that you are presenting to us? So, and if you are, what elements of your search will be left for others to better your process, so this doesn't die out? You know, it will have a continuity improvement to reach the final stage of what your vision was.
Yeah, so I would say this area of fabricating perovskite on flexible samples specifically is not very well researched at this moment. I'm not the very first person to do it, but I'm one of the first people to do it. So that's why there's so many difficulties and trial and error in this research process. As far as what would be left after I complete my goal, I guess in engineering, you can really improve on you can improve all the time on anything. There's no really limit to what can be done. I would say maybe it would be interesting to see maybe how because I use like a flexible substrate that was specifically called PET. I know there's different flexible substrates called PEN and other ones, so maybe if they could figure out a way to translate maybe the perovskite onto those flexible substrates, because there's different types, I think that would be really interesting to see and discover what might be different in my fabrication process versus the supposed other fabrication process. Yes?
You were part of this nanotechnology program last summer, and that was your first experience with a lot of the equipment and the people and the processes. What did you take from last summer that gave you a head start to be successful with what you did this summer? Did it relate? Can you talk a little bit about that?
Yeah. So last year I did my project on boron nitride and diamond electronics. It was a little bit different because I was in a clean room setting, and that's more monitored and strict rather than to being in just a regular lab, which I was in this year. However, in this clean room setting last year, I still watched the spin coating process go on, and there was a little bit differences. They were working on different patterns, and they were Oh, and they also took the same measurements I did. So they actually also had an IV curve last year, which determines whether the device is acting as a resistor or a semiconductor, like I explained earlier. But that was really interesting. That was kind of similar. But what I took from that is I really like hearing what other people have to say and their ideas, and really truly being open to any changes or recommendations that can be made. Also, there is so much trial and error, and I know I just mentioned that just previously in the last couple of questions, but I feel like research is always a trial and error over and over again. So just being okay with not getting it right the first time. So yeah, and also just being supported by everyone around me. It's just really great. My graduate mentor, my faculty mentor, Jessica, and just presenting research. It's a very different area to present in. You have to explain the process, but also the bigger picture. So I think I learned that from last year.